Hello, welcome back to Algebra 2. This is lesson 7, and we're having a lesson on function composition and inverse functions. This is probably going to be pretty new to most all of you, but this is an extremely important concept, and you've been using it before. You just didn't have this kind of vocabulary for it. So we call something composed of something else if f is composed of g if g is inside of f. In other words, f is made up of g. And we can build more and more complex functions by putting functions inside of other functions inside of other functions. So I'm going to start with kind of an abstract representation. This is how you would write, or one of the ways that you can write f composed of g. We just put f, and then in the parentheses you put g of x. Now, the function, the domain here is of x. So this is my domain, and this function here, this is f, and f will map the x values. I'm sorry, this is not f, this is g will map the x values to this g of x here. Then f is going to map those values of g of x over to f of g of x. So a number gets mapped by g over to its range, which then gets mapped by f to the final destination. All right, let's take a look at a couple of examples now that have some numbers in it, right? All right, I've got f of x is equal to x squared plus 3x, and g of x is equal to x plus 1. We want to find f of g of x. So what I do is I take f, and I put g into it. So everywhere I see an x, I put x plus 1. And that's going to go right there. And I'll need parentheses. So f of g of x is equal to parenthesis x plus 1 squared plus 3. And then we could work to simplify this a little bit, but we'll leave that for another day. Let's go to g of f of x. So g of f of x is when I take f. Let me rewrite them right quick. So f of x, remember, is x squared plus 3, and g of x is equal to x plus 1. We just did f of g of x. Now we're doing g of f of x. So f is in the inside of g. You can see that, how f is inside the parentheses of g. That tells me that it's going to go right here, where that x is. And since it's just addition, I won't need to put it in parentheses, but I certainly can. X squared plus 3, and then I have plus 1. And we can go ahead and simplify that one. That one's easy. X squared plus 4. Okay, so now I've got time for you to do a practice problem. So if you would please go ahead and work practice 7.1. Pause the video while you work it, and then we will go over it. Okay, hopefully that wasn't too bad for you. Let's take a look at it. So f of g of x, we are going to take, since g is in the inside of f, we're going to take what g is, and we're going to put it right there. So I have 2 parentheses x plus 3 over 4, and then a minus 1. And, you could leave it like that for now, or maybe you simplified. You realize that 2, this 2 can reduce with this 4. 2 goes into 2 one time and 4 twice. So this is x plus 3 all over 2 minus 1. And we could probably even combine like terms and go further, but I'll stop there. All right, now we have to put f inside of g. So g is x plus 3, so the x became a 2x minus 1, but then I still have a plus 3 and all over 4. So then this becomes, if you allow me to go ahead and simplify, negative 1 plus 3 is 2 over 4. And we could even simplify that some more, because I can divide each term by 4, and I get 1/2 x plus 1/2, or you could leave it like that. Either one is fine. This is not a simplifying lesson. This is about function composition. One thing I want to point out is that in general, f of g of x is not, f of g of x is definitely, in general, not equal to g of f of x. It can be. It can be equal to it, but it's just not in general. And interestingly enough, you'll find, I think, that these two equations actually are the same. If you simplify this down, this one ends up being the same. So they can at times be the same, but if you refer back to our previous example, they were definitely not. We got x plus 1 squared plus 3 versus, x squared plus 4. Those don't at all work out to be the same if you multiply it out. So let's go on. So just keep that in mind, that some functions, when you compose them, they end up giving you the same result no matter which direction, but in general, they are not equal. Okay, oh, we already looked at that. Let's take a look at our next practice problem. Okay, so I've given you a table of values, and I would like you to evaluate f of g of 3 and g of f of 10. So go ahead and give that a try. Okay, so f of g of 3. So remember what's going to happen here. When you compose f of g of x, what's happening is g is going to go first and move the x to g of x, and then f is going to move those over. So 3 is an x value. G is going to map 3. You can see from the table that G maps 3 to 20. Then we got to go over here and find what F maps. Well, F maps 20 to 8. So that is the same as, let's just do it in in 2 steps here. G of 3 was 20. So G of 3 becomes 20. And then F of 20 from the table is 8. Now we're going to do it a different way. We're going to do F first this time. F of 10 is 4. And G of 4 is, well, G of 4 is 10, so it mapped it right back. This begs an important question. What if I had asked you to do something like f of, let's see here. How about g? What if I asked you to do g of f of 12? If this is the entire function, we would have to actually say that this was undefined, because g f of 12. Oh no, I'm not f of 12. I'm sorry. F of 30. Sorry, f of 30. F of 12 is undefined as well, but because 30 is in the domain of f, but it maps to 12. But 12 is not in the domain of g. So when you do function composition, you can see that sometimes you'll be able to go the first trip, but then you end up in a place where it's not in the domain of the next function and it doesn't work. So function composition can have some limiting effects on your domain. All right, I have another practice problem for you to do. We've seen function composition with tables of values. Let's take a look at it with some graphs. And I apologize that these graphs are so poorly drawn, hastily drawn. And please just kind of estimate the nearest values if you can. Call them whole numbers. All right, let's give it a try. Okay, f of 0 is 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, about 7. G of negative 2 is about 1. What is g of f of g of 1? Well, g of 1 is, I guess, negative 1, right? So this is f of negative 1. And f of negative 1 looks like 6. What about g of f of 3? Well, f of 3, 1, 2, 3 is 0. So this is really g of 0. And I told you to round the nearest whole number, and so maybe you rounded that one, but I will actually say that's just negative a half. I think that's what that is. Okay, so that's graphs and tables with function composition. All right, I have another example to share with you. All right, I've got f of x is equal to 5x minus 1, and g of x is equal to x plus 1 over 5. Let's find f of g of x. So f of g of x is equal to, I need to put g into f. So I have 5, and then the x gets replaced with g. Minus 1. Okay, when you multiply a whole number times a fraction, always divide first if you can. 5 divided by 5 is 1, and 1 times x plus 1 is x plus 1, and then I still have a minus 1. And x plus 1 minus 1 is simply an x. So that's interesting. F of g of x became an x. Now we're going to find g of f of x. G of f of x is going to be taking f and putting it into g. So wherever there's an x in g, we're going to put at 5x minus 1. So 5x minus 1 plus 1 all over 5. Minus 1 plus 1 makes it a 0, so this is 5x over 5, which reduces to simply x. So f of g of x is x, and g of f of x is x, which is of real interest because what that shows us is something very important. That will only happen when g of, let me put it in the terms of the notes, because f of g of x equals x and g of f of x equals x, f and g are known as inverses. Pictorially, what we're saying is that if we have a domain x and we apply g to it, we go to g of f of x. Sorry, g of x. But then when we applied f, instead of going to some new range, it actually, when we applied f, it brought us back to the x that we started with. Say, if you put in g of x, you get x plus 1 over 5. But you then put that into f, you get x back. Likewise, if I start over here with the x's of f, and I map them over here, g takes them back to x. So they are inverses of each other. Not all functions have inverses. They must be what we call 1 to 1. To tell if a graph of a function has an inverse, you can use what's called the horizontal line test. We've talked about the vertical line test, right? Now you've learned about the horizontal line test. The horizontal line test, it works because when you find an inverse, all the x's and y's will switch. So because the nature of an inverse is it takes your y back to x. So if your function does not pass a horizontal line test, then when you invert it, those horizontal lines are now vertical lines. So the inverse would not pass the vertical line test. So that's how we can tell if a function has an inverse. We know it's a function if it passes the vertical line test, and we know it has an inverse function if it passes the horizontal line test. So if a function has an inverse, we'll usually denote it as f to the negative 1, which means f inverse. It is not an exponent. It is a notation. So just keep that in mind. We'll learn about the negative 1 exponent. You may have learned that it means move to the denominator. That's not what that is. That's not an exponent. That is f inverse. Inverse functions f and f inverse have the following characteristics. They have their x and y coordinates swapped, as we just mentioned. They are reflections of each other across the line y equals x. F inverse of f of x equals x, and f of f inverse of x equals x. If f has an inverse f inverse, then they are inverses of each other. So if f and g are inverses, f inverses g and g inverses f. The range of f is the domain of f inverse. And that is extremely important. Let me draw that again. So if I have a function, x, and I map it to some range called f of x, that is the domain of f inverse. And we'll see how that works out, because it makes that fact makes a pretty big impact. All right, I got some examples here. So let's graph the inverse of the following functions on the same axis. So we can do this in one of two ways. We could graph the line y equals x. We did just mention a moment ago that inverses are reflections across the line y equals x, but we also talked about how the x and y coordinates are swapped. So let's look at both ways of doing that, and we'll see how they work out to be the same thing. So the coordinates of this point here are -1, 2. So we have a point on f of -1, 2. Well, then on f inverse, then we should have 2, -1. So I'm going to go to 2, -1, and that's the inverse of this point. Now, this point here is 1, 3, so its inverse is at 3, 1. This point here is at 4, 1. Its inverse is at 1, 4. This point here is at 3, -1. Its inverse is at -1, 3. I mentioned that they need to be reflections across the line y equals x. The line y equals x will simply go right through the origin at a 45-degree angle, up 1 over 1. And I think you will agree with me that this plotting both f and f inverse on the same graph, you end up with this mirror reflection, this symmetry going across this way. All right, let's try this next one. All right, so let's just get some of these key values. This point here is like -4 and what is it? -4 and maybe -2. So I'm going to go the -2 and -4, and it's actually a little bit more than -2, so it's probably like right here, but we could round if we want. All right, this point here is 0, 1, so I'm going to plot 1, 0. This point here is 4 and a little bit more than 4, so I'm going to go a little bit more than 4 and 4. So right there. All right, this is not quite enough for me. Let's plot a few more points. Here's -1, -1. Oh, well, if I flip-flop -1 and -1, I get -1, -1. Right? This point here is 1, 3, so I'm going to plot 3, 1. All right, this is starting to shape up for me a little bit, but what I'm going to do is I'm going to aid myself by going ahead and graphing the line of symmetry, and I think that's going to help me do what I need to do. So you can see I'm reversing some of the points, but I've got so many of them, and I want to get the shape right that I think it's going to help me kind of see, okay, so that's going to go here. It's going to cross just a second here, then come down, and then it has to come back again towards here. What do you think? Did we do an okay job there making it look right? It's not perfect, but that'll work. All right, you have a practice problem. Give it a shot, pause the video, and then we'll discuss. Okay, the function f consists of only the values in the table below. Make a table of values for f inverse. So this is f, so let's find f inverse. So remember, the domain of f inverse is the range of f. So this here is my domain of f because it's the x values, right? And this over here is the range. So I'm going to put these values here. And then I'm going to put these values over here. Okay, that's it. Also, you could think of it, we're just flip-flopping the x and y. So 7, 6 became 6, 7. -3, 2 became 2, -3. All right, now we've talked about how to find the inverse given a graph, given a table, listing of points, dots, what have you. The last thing is we got to do it algebraically. So let's do it with an equation. And it turns out the process is actually remarkably similar. So we're going to find the inverse of each function, and we'll confirm it using function composition. Remember that f of f inverse should give me x back, because that's what an inverse does. It takes you back to the domain. So we're going to confirm that. All right, I've got f of x equals 3x plus 1. That is the same as y is equal to 3x plus 1. So we're going to let y be our f of x, and that's going to help me out. I love function notation. Normally, this is one time where I take it out. So now what I need to do, remember that in an inverse, the x and y's are flip-flopped. So what we're going to do is we're going to replace the y with x and the x with y. But everything else is going to stay the same. Now, there's nothing algebraic there. I'm not saying these two equations are equal. I'm saying they're inverse. So that's what I call the invert step. That's me inverting the thing. And in fact, this is the inverse. It's just not in function form. To get in function form, we'll simply solve for this. Okay, now that I've inverted, I just need to solve this for y. So I'm going to subtract 1 from each side. And that will give me x minus 1 equals 3y. And then I'll divide both sides by 3, giving me x minus 1 over 3 is equal to y. And I'll write that in inverse notation. We're saying that is f inverse of x is equal to x minus 1 over 3. And let's check our work. We're going to check our work by using f of f inverse of x. We'll see what that does. So the f of f inverse means I need to replace x with f inverse. This x minus 1 over 3 needs to replace the x in the original function. So instead of 3x, I have 3 times x minus 1 over 3. And then plus 1. Okay, I multiply. 3 divided by 3 is simply 1. So it just, remember, you multiply a whole number times a fraction, divide first if you can. 3 divided by 3 is 1. And 1 times x minus 1 is simply x minus 1. And then x minus 1 plus 1 is simply an x. All right, that's one check. Let's check the other way. F inverse of f of x. Well, f inverse of f of x means I need to put f, 3x plus 1, where there's an x in f inverse. So I put 3x plus 1 where there was an x, then minus 1 all over 3. The 1's cancel out. I get 3x over 3, which is simply x. So as you can see, we've checked and confirmed that they are inverses using function composition. Okay, I'm going to get rid of this, though, because it's going over to my next step. So I'm just going to scroll down here, and we'll do it again. All right, I'm going to find the inverse of this function. So to find the inverse, first thing I'm going to do is rewrite this in terms of y, because I find that easier. And now I flip-flop the x and y. So the y becomes an x, and the x becomes a y. And that's the invert step. This is the inverse of this, because I flip-flop the x and y's. But I need to solve for y to get in function notation, so I'll multiply both sides by 5, and I get 5x is equal to y minus 1. And then I'll add 1 to both sides, and I get 5x plus 1 is equal to y. So we now have that f inverse of x must be 5x plus 1. So let's check f of f inverse of x. So f inverse is 5x plus 1. I need to replace x with that. So 5x plus 1 minus 1 over 5 gives me 5x over 5, which is simply x. Now let's try f inverse of f of x. Well, that is where I put x minus 1 over 5 everywhere there's an x. So I have a 5 times x minus 1 over 5, and then plus 1, right? So the 5's reduce, and I'm left with x minus 1, and then plus 1, and 1 minus 1 is 0, so it's simply an x. And we've done it. All right, so I think you have one more practice problem before your lesson's exit ticket. So give it a try. Here's the problem if you don't have it in front of you. Pause the video if you haven't yet and do it. Okay, let's go over your answers. All right, I have 5x minus 8. So to find f inverse, I need to flip-flop the x and y. So this becomes an x, and this becomes a y. I'll now solve for y. And I'll divide by 5. I now know that f inverse of x is equal to x plus 8 over 5. So then I have to check by function composition. So let's do f inverse of f of x first. So I'm going to replace the x in f inverse with f of x. So x plus 8 will be 5x minus 8 plus 8 all over 5. The 8's go away, and the 5's reduce. All right, let's try f of f inverse of x now. We got to try both ways. We will see later on that there'll be times where they work one way and not the other, and you don't have a true inverse. So we have to put x plus 8 over 5 where the x is in f. So this becomes 5 times x plus 8 over 5 minus 8. And so the 5's reduce. And I get x plus 8 minus 8, which is just x. Super. All right, let's do the next one. I've got g of x equals 4 times x minus 1. So this is my y, and that's my x. So I need to flip-flop them, making this x equals 4 times y minus 1. And I'll solve for y. I am going to divide both sides by 4 first, I think. Actually, that's kind of a... as long as it's factored out like that, I can do that. And I get x over 4 equals y minus 1, and then I'll add the 1 over. So I get x over 4 plus 1 is equal to y. We could do that in either way, though. So I know that g inverse of x is equal to x over 4 plus 1. All right, let's check g of g inverse first. So I need to put g inverse in for g. So I get 4 times x becomes x over 4 minus 1. And I'm sorry, x over 4 plus 1. And then I have a minus 1 from there. And so there we have it. So x over 4 plus 1 went in for x, and then I still have the minus 1 in the parentheses before. Okay, just double checking there. All right, the 1s are going to cancel out, and I'll have 4 times x over 4, which is just x. And g inverse of g of x will become, all right, I got to put g, 4 times x minus 1, in for x here. So I'll get 4 times x minus 1 all over 4 plus 1. This time these 4's cancel out. I get x minus 1 plus 1, which is just x. All right. So you do have an exit ticket today to think about and take with you as you continue to do your homework and your studies and to explore. So I've got an opportunity for you to graph both of these, confirm that they're inverses by graphing the line y equals x, making a table of values of 4 different x values, and then finally check algebraically with function composition. Okay, so that's it for this lesson, and I'll see you next time.